Thus, though u0 have two values, u1 can have only one value corresponding to both the values of u0, either plus p or minus p. u1 has value minus 1 by 2p dp by dx, because when p is, say, u0 is minus p, then minus dp by dx and 1 by 2 into minus p will be making it again, say, minus 1 by 2p dp by dx, the same as the value of u1 corresponding to u0 equal to plus p. However, due to the two different values of u0, u1 can have two different values. I mean, u can have two different values. U equal to u0 plus h cross by I u1 can have two different values. We represent them u plus and u minus. U plus is u0 plus h cross by I u1 corresponding to u0 equal to plus p, and u minus is u0 plus h cross by I u1 again corresponding to u0 equal to, say, minus p. So u plus equal to u0, you substitute p plus h cross by I u1. u1 is minus 1 by 2p dp by dx. So that is p minus h cross by I 1 by 2p dp by dx. We will rearrange this. See, 1 by 2p dp by dx is the derivative of natural log root p. Natural log root p is 1 by root p into root p has a derivative. See, d by dx of natural log root p. Natural log root p has a derivative. Derivative of logarithm 1 by what is there inside the logarithm, that is 1 by root p, and derivative of root is, derivative of root x is minus 1 by 2x root x, minus 1 by 2 root x. So this will have a derivative minus 1 by 2 root p. Make it overall having a derivative minus 1 by 2p. That is 1 by 2p dp by dx is there. So absorbing this minus, we make it, say, p minus h cross by I d by dx of natural log root p. Root has a derivative 1 by 2 root x. I think I have put a minus additional here. This only, say, 1 by 2 root p. So this is p minus h cross by I d by dx of natural log root p. Similarly, u minus equal to, you substitute u0 equal to minus p minus h cross by I u1 is once again minus 1 by 2p dp by dx. So this is minus p minus h cross by I d by dx of natural log root p. So we have two different values of u being obtained. But we know that u equal to dw by dx. And we are interested in w in order to write the WKB Wave function phi as phi equal to e raised to I by h cross w of x. W could be obtained from this one as the integral of u over dx. So w equal to integral u dx. Therefore, phi equal to e raised to I by h cross w of x equal to e raised to I by h cross integral u dx. That is exponential I by h cross integral. U has two different choices, u plus and u minus. Corresponding to u plus, we write the solution as, say, phi plus, and corresponding to u minus, we write the solution as, say, phi minus. Then phi plus equal to e raised to I by h cross integral p minus h cross by I d by dx of natural log root p dx. That is e raised to I by h cross integral p dx minus integral d by dx of natural log root p. I by h cross and this h cross by I will be vanishing for the second term. I might have put this a different exponential. Anyway, this is now e raised to I by h cross integral p dx. That is being kept as it is for this part. However, e raised to integral d by dx of natural log root p is e raised to minus natural log root p. Integration vanish with, or integration will be cancelling with this differentiation to make it say e raised to minus natural log root p. So this term becomes e raised to minus natural log root p into this is retained as it is e raised to I by h cross integral p dx. E raised to log x is x itself, so e raised to minus log x is 1 by x. So this is 1 by root p e raised to I by h cross integral p dx. Similarly, you substitute u minus to obtain 5 minus as say, here this will be minus going minus and this term will be retained. Here you will have a minus sign, 1 by root p e raised to minus I by h cross integral p dx. Now we make use of the superposition principle. If there are two different possible solutions, the most general solution will be a linear combination of the two, as long as the solution or the wave function or the fundamental quality of wave function in quantum mechanics is concerned. It always satisfies the superposition principle. So the overall WKB wave function can be written as a by root p. So this is the first solution and this is the second solution. We take a linear combination of these two solutions and write down the most general solution with a and b being the expansion coefficients. A by root p e raised to I by h cross integral p dx prime plus b by root p e raised to minus I by h cross integral p dx prime. So this is the general format of the WKB wave function. So once we come across a problem where we can apply WKB method, very shortly I'll tell you what are the qualities of such problems where the semi-classical approximation will be most effectively valid. We will be able to write the wave function representing the system in this format. For this we require a knowledge about the magnitude of the momentum possessed by the system. So once you know, so I have 2 points to make here. The first point, once you know the momentum possessed by the WKB system, you will be able to write down the wave function representing the WKB system or the system under your study in this format. Just put a by root p, where p is the momentum, e raised to I by h cross integral p dx prime plus b by root p e raised to minus I by h cross integral p dx prime. And the second point is that look at the momentum. Or the wave function is being written in terms of an exponential function involving momentum. However, the momentum is given by p equal to square root of 2m into E minus V, where E is the total energy and V is the potential energy. We come across classical systems such that the total energy possessed by them exceed the potential energy. Then the quantity within this square root is positive. That means the momentum possessed by the system will be real. However, there could be some situations, not some situations, most often there are situations where the potential energy exceeds the total energy. So that E minus V will be negative, making the momentum possessed by the system negative. Making the momentum possessed by the system negative within the square root, that is imaginary. So the momentum can be real provided the system is a classical system. However, in the case of a quantum mechanical system, the momentum can be complex or imaginary. And depending on that, the WKB wave function can also have two different mathematical formats. Suppose this is real, then the exponent is e raised to I into a real quantity. That can have a de Moivre's expansion e raised to I theta equal to cos theta plus I sin theta. So under such a situation, that is under the situation where the system is a classical system or purely a classical system, the WKB wave function will be represented in terms of cosine function and sine function, and such a wave function always represent an oscillatory system. So there is a chance that the WKB wave function representing a system may be an oscillatory solution. However, in the case of a purely quantum mechanical system, this parameter in the integral in the power of the exponent term can be imaginary. So there can be an additional I coming from the momentum, making the exponent, the power of the exponent as say I square, which is minus 1. So then it will be e raised to minus, and here this can be e raised to plus as well. That cannot have a de Moivre's expansion, and under such a regime, the wave function representing the system will be either an exponential decay, exponential fall, or an exponential growth. So the WKB wave function can have two different choices. For pure classical systems where the momentum is real, the wave function will be oscillatory, represented in terms of cosine and sine functions. And in the case of a purely quantum mechanical system, the wave function will be exponential. Most often it will be representing an exponential fall, as this is also something we have seen several times. Hence, in fact, a quality of the quantum mechanical wave function. For such a system, the total energy will be less than the potential energy. Once it is the situation, the probability for finding the system in such a regime will be diminishing exponentially. So this idea is also consistent with the general WKB wave function that we have derived. So this is about the WKB wave function, or the representation of a WKB system using a general wave function. The wave function, you just recall it, a by root p e raised to I by h cross integral p dx plus b by root p e raised to minus I by h cross integral p dx. Now we'll see some physical situations where we will be able to apply WKB method and some general mathematics that are to be derived in the case of such situations.